Recorded is rolling. It's Wednesday, March 5th. So we're going to continue our review. I know this week we're reviewing, we're going over a lot of fundamental type puzzles that you guys are going to see on the exam. I think probably next week and going forward, I can kick this up a little bit. I think told you guys my plan next week is to throw some in-class quizzes at you guys and have you guys work in teams on those. Right, so I got that, but right now we're just doing this review. And I want to keep this week a little bit laid back because I know a lot of you guys are focused on, well, tomorrow's the SAT. So you guys know Google Classrooms is exactly where you're testing, and also relocations. Here's my own relocations for my own first 4 classes because there's testing in this room. But if you want to know relocations for other classes, if that's relevant to you, that's also in Google Classroom. All right, so you guys got all that? All right, so also before we jump into this review, let me fill you guys in on what my other classes are learning. So I'm teaching them about refraction. There's announcements. Wait, pause this. All right, recording resume. We're back. So my other classes learning about refraction. So I gave them these prism pieces and some lasers yesterday. You guys see, now this laser light can just go in a straight line, of course, but when it hits this, this prism, look, it's gonna bend. You guys see it's like bending, right? You guys ever put a straw in a glass of water? It looks like it's bent, but thank you. It's not really, right? And so how much this is going to bend in the physics term for that is called refract. How much is going to refract? Well, it depends on how much light slows down inside this material. So the fact that light slows down kicks off a process that causes it to refract. Right? So the speed of light in a vacuum is 3 times 10 to the 8 meters per second, but it's slower inside glass, inside water. Right? Oh, hey, you can see the refraction there too. See it like bending through. See it, warm. Okay. Right. So how much it refracts, you can find with something called Snell's law. Right? Or if you measure the angles, because I had students take out some protractors yesterday and actually measure the angle when they were trying to laser through the prism. You can back calculate what is the index of refraction of the glass piece. That was actually one of the goals I had from yesterday. It's called Snell's law. Right, and then one more of these. Oh, you guys see this fish down here deep in the ocean? So this fish is sending out like a billion different rays of light, all different directions. And I have 4 of those rays of light mapped here. So a ray of light that goes straight up, it's just going to keep going straight up into the air. Right? It's some angle. Okay, it's going to refract a little bit going from the water into the air. Okay? But do you guys think at some point that this refracted angle going from the water into the air is going to approach 90 degrees? Right? And the angle on the side of the water that's associated with that is called the critical angle. Now you can also shine a light beam going the other way. Like if I shine a laser light going this way, it's going to refract to go down and hit the fish this way. Okay. If I shine a laser light that's like almost horizontal to the water and it hits the water surface, it's going to refract down. At the critical angle. Is it? Okay. So anything beyond that, beyond the critical angle, no longer refracts. It's called total internal reflection. It's the title of this one. Okay. And guys, you guys see that fisherman trying to get this fish? Where does this guy see the fish? It's really hard to see the fish, right? Because if he looks straight at it, no way does he ever see it, because there's no light beam that travels straight towards the fish or away from the fish towards the fisherman. But do you think maybe there's a little ray of light that travels like right about here and then breaks across the water and goes like a 1 degree from, or like almost parallel to the water and then enters his eyes that way? Right. So probably like this. And then if the fisherman sees the ray light coming from that direction, he says, oh, well, it looks like the fish is over here. And he thinks the fish is maybe just below the water, like way off over here. This is where the fisherman thinks the fish is. Of course, the fish is actually way down deep in the ocean. All right. So there you go. All right, there's some pool physics if you're ever swimming with your friends in the pool. But hey, how'd your legs get so short? Not really. It's refraction. All right, so of course you guys have paper for notes. We're doing some review here. Let's go through all these variables. Now we're moving on. Actually, we hit a pretty good pause point yesterday. You guys remember yesterday we were doing some Atwoods, but actually we took all day yesterday to do Atwoods. We look at classic Atwoods, modified Atwoods, what's the acceleration, what's the tension in the string. Right, so those type of questions. There's some kinematic tie-ins, right? How far, how fast does it move after some interval? Okay, so now we're moving on to I had this written up here too. Circular motion, gravitation, and orbits. Now, last year, AP used to categorize this as Unit 3. This year, they've also thrown this in with unit 2, which also includes all the output stuff. So I don't know why, but anyway, I don't know if that even makes a difference. Okay. But guys, what is theta in physics? Aha, angle, right? And if this was a turntable, I had a turntable here, could that be angular displacement? I think I got a picture of this coming up soon. Let me flip ahead a little bit. There you go. All right, you guys remember this turntable? This turntable? You guys had some turntables. What does this omega mean?
Angular velocity.
Aha, angular velocity. Right? Sometimes you hear called rotational velocity. Right? Oh, and units. Whoops, units. Could you measure how far something's turned in radians? Could you measure how far something's turned in degrees with a protractor? Yeah, you could. But when you get to the formulas, isn't it better to use radians? Right? We get to the turntable physics book. Right. Right. And then radians per second for angular velocity. What is alpha in this context? Angular acceleration. You guys, what does that mean? If something has an angular acceleration, what is it doing? Yeah. Yeah, it's changing how fast it's spinning. Maybe it's speeding up spinning, maybe it's slowing down spinning. Right? Maybe positive or negative. Right. Oh. All right. Then there was I got a couple of gold rows here. What do you think AP stands for?
Centripetal acceleration.
Aha, centripetal acceleration. So if you're in a rotating frame of reference and you close your eyes, it feels like you're accelerating even if you're not speeding up, right? Because you're changing your direction. Now, yeah, meters per second squared, so still acceleration. And then F sub C, centripetal force, right? So what force is holding you in a circle, right? Now, guys, centripetal force. If you have to, suppose you get some rotational situation and you're asked to draw a three-body diagram. Are you ever going to label a force? Oh, this is centripetal force, F sub C. Do you ever do that? The answer is no. Right? Now, other kinds of forces can provide the centripetal force. Could it be possible? Could a string tension provide centripetal force?
Yeah.
Yeah, if I had like actually I got this right here. If I got a string and I tie this onto here and I whirl around circles, I bet there could be some tension in the string holding this in a circle, right? That could provide centripetal force, right? Guys, what if there's a car going around a bank? Like here's a banked road and there's a car going around, right? Like a Daytona 500 banked wall. Okay. Is there a normal force from that wall?
Yeah.
And here, guys, see if you guys get this has been a question in the past. Does the full normal force provide centripetal force, or is it only the horizontal component? Yeah, just the horizontal component of that normal force provides centripetal force. I've seen that be a question in the past. Right? So, how about this? A satellite's going around the Earth. Guys, satellite going around the Earth. What force is providing the centripetal force? Gravitational force. Aha. Right. Right now, the bottom half of this poster is really a different unit, but we'll knock these out anyway while I got this out. So by the time we get to it, what does capital I stand for in a rotational sense? Yeah, rotational inertia. Okay, it's got these units, kilogram meter squared. What does the tau stand for? Torque. What does the capital L stand for? Yep, angular momentum. Okay, and if you have a change in angular momentum, right, that could be angular impulse, like that. It's got these units. All right, so you guys good with this? All right, I have a pretty similar one for analogous variables. So everything we did in linear has some rotational analogous part. Well, time is still time. That one's the same. But that's the only one that's the same. Okay. Now, instead of how far something moved in meters, we want how, what, and what. How far it's turned in radians. There you go. Right. It could also be degrees, but the formula is good to use radians. Okay. Instead of linear velocity, we got, yeah, there you go. Omega angular velocity radians per second. Right. Instead of A, we got alpha. Instead of M for mass. Right, okay, now this is like a rotational dynamics. You won't see this one very much later today, but somehow mass distributed called rotational inertia. Okay. Guys, what's the is this Newton's second law of motion? F equals ma?
Yeah.
Okay. What is the rotational form of that? Aha, torque equals I alpha. Okay. Now really it's a net torque. So now torque is R cross F. Okay. And if I want to say I alpha, it really is the net torque. So if there's multiple torques going on, if there's like some frictional torque subtracting off, right, something like that, I have to find the net force. Same thing with this one. This would be net force, net torque is I alpha. What's the equivalent to? Actually, what does this say? This says what equals momentum. Is mass times velocity. Is that L equals I omega? Okay, angular momentum. Okay. And then, what does this one say? Kinetic energy. 1/2 mv squared, mass, speed, whatever. And then does that go like, what if there's a ball rolling across the floor? You have to consider, well, it also has energy in this mechanical form too. Okay, remember this? All right, what's next? Let's go to turntable physics. So got a turntable. I give it a little spin. It's moved so far. If you know how much time it took, it's spinning so fast. And maybe it started from rest. Maybe it's speeding up spinning. Maybe once it is spinning, maybe you let it go and maybe it slows to a stop. That would be some kind of acceleration, angular acceleration. Okay. Now, guys, is how far you've walked around a circular racetrack related to like how far this turntable's turned?
Yeah.
Okay. But it also depends where you're standing. Because if you're standing right at the middle, you could be spinning really fast, but you're not really moving in any distance, right? If you're standing like 1 centimeter out, you'd be spinning equally as fast, but okay, now you moved a little distance, right? Now you've moved kind of medium distance, right? And then way out here, now you've moved a long distance, like the circumference of a circle, okay? So, guys, I covered up 3 formulas. Can you guys write these 3 formulas? You guys know what 3 formulas I'm covering up here, right? Because I keep pulling out that poster about every week. Okay. Go ahead, write those 3 formulas I got covered up. That could tell you something about displacement, velocity, and acceleration. Can you relate the angular motion, like the turntable turning, to a linear motion? Like if you're like how far have you gone around a racetrack, how fast, and acceleration. Okay. So displacement, velocity, and acceleration. What is the relationship? Going from turntable physics back to linear physics. Or vice versa. Maybe you have linear and you want to figure out what is the angular type motion. Okay. All right, you guys got those 3 formulas? What's the first one? X equals theta r. Okay. Now, guys, the key is if you plug in theta, yeah, suppose I measure this angle. Say, okay, this angle's like 30 degrees with the protractor. Okay, I'm going to go 30 degrees. It just makes that up. Okay. Can I plug 30 into this theta?
No.
The answer is no, right? Because I have to convert to what first?
Radians.
Radians. How do you convert? Here, guys, suppose the answer, suppose this was 30 degrees. How many radians would that be? I don't actually know right now, but I could figure it out. I got 30 degrees. Guys, how do I convert to radians? There you go. That's a good way to do it. Divide by 180 and multiply by pi. Because I know halfway around the circle would be 180 degrees, and that's also pi radians. Right, you guys know that too? Or you could, alternatively, you could divide by 360 and multiply by 2 pi. All right, so that would be the same thing. This looks like 0.52 radians. Okay? That's hard to show. 0.52 radians. So 30 degrees is the same thing as 0.52 radians. You guys got that? Okay. Oh, yeah.
Divide by 360 and multiply by 2 pi.
Yeah, that would be the same thing. Here, I can show you guys. So 30 degrees, if I divide by 360 for the full circle and multiply by 2 pi, yep, it's the exact same thing. Exact same thing. Yeah. Oh, how about this? Have you guys, I think you guys just know a specific version of this formula since elementary school. And how does it go? What's the elementary school version of this one? Circumference, which is exactly 1 trip all the way around circle, is 2 pi r. Aha. Because 2 pi radians is also a trip around circle, isn't it? Aha. Okay. What's the velocity one? Omega times r? Okay. So if you know how fast this is spinning in radians per second, and you multiply by your location from the center, that'll tell you like the radar gun speed. Doesn't radar gun tell you like miles per hour, meters per second, how fast? Right? Like an instantaneous speed, a linear speed. So, okay. And then there's also an acceleration version. So if it's speeding up or slowing down spinning. Okay. Right. This one, I know I keep pulling up this poster all the time because it seems like it has a lot of applications. Do you guys know this? Okay. Guys, write the 3 rotational kinematic formulas. Go ahead, write this from scratch. 3 rotational kinematic formulas. Here's a hint. It's the same as the 3 linear kinematic formulas, except you just pop in the rotational variables. So see how you guys are doing. Can you guys write the 3 rotational kinematic formulas? The first one starts theta equals. So that's your first one. Theta equals something. You guys are off to a pretty good start. All right. You guys tell me, what'd you write for the very first one? Theta equals what? That's it. Omega t, not t plus half alpha t squared. This is analogous to x equals v naught t plus 1 half a t squared. Okay. Like guys, if there was no alpha, that would mean that the turntable is not accelerating, right? Wouldn't that just be, oh, look at that, distance equals speed times time, right? Like if you're cruise control on a car I know it's linear, but it's the same idea. It's turntable, right? Hey guys, is the Earth turning at a constant angular velocity? Right,
Yes.
24-hour, well, one rotation per 24 hours. There's a way to convert that to radian per second, right? Okay, so then if you put like 24 hours in here, I bet you can get like one rotation, right? Now, if it is changing how it's spinning, speeding up or slowing down, right now you got this bit, it's 1/2 alpha t squared, and then you can put it all together and get that. What do you guys write for the second formula? Aha, right. How fast it's spinning is how fast it was spinning plus alpha t. Right? And what do you write for the third one?
Squared equals initial squared plus 2 alpha theta.
Ah, got it. All right, 3 for 3. 3 for 3. Okay. And of course, if I put these next to the linear formulas, they look pretty much the same. Right, just here's linear, here's rotational. All right, you guys good with the kinematic formulas? Okay. All right, let's apply these in a graphical sense. All right, here we got turntable slows to a stop. And I want you guys to create the 3 kinematic graphs. So here, I'll give you guys the vertical axes. I got theta, omega, and alpha. Now, these are all as a function of time. So put time on the horizontal axis for all 3 of those. Theta versus t, omega versus t, alpha versus t. Right? And then draw the graphs. What do those graphs look like for a turntable? So I should say uniformly. A turntable slows uniformly to a stop. So just real basic scenario. Turntable slows uniformly to a stop. What do those 3 graphs look like? Turntable slows uniformly to a stop. Okay. Give you guys a little hint. When it's slowed to a stop, what's happening to the angular velocity? It's slowing down. In fact, it slows all the way to what number? 0 would be a stop, right? Okay, so that's okay. Now that's a velocity concept. What about a displacement concept? Now, while it's slowing to a stop, is it still rotating forward?
Yes.
Yeah. So is it still accumulating positive angular displacement?
Yes.
But maybe at a slower and slower rate, right? And if I say uniformly, slows uniformly to a stop, they always throw in that word, really. Then what do you know about acceleration? Yes, some kind of constant value. Right? No, it's non-zero, but it would be constant, wouldn't it? Right? Right. You guys put those all together? Right. You guys ready for the answer? Ready? Bam! That's what you should have drawn right there. So I got an upside down parabola. Guys, where's the vertex of this parabola? Is it at the bottom or is it at the top here? Yeah, here's your vertex right here. Here's the vertex of the parabola. Okay. Like an upside down parabola. Okay. And then omega versus t, you got linear with the negative slope, and then alpha is the negative constant. Okay. You guys get those. Okay. All right. You guys remember that experiment with the Play-Doh canisters and the PVC pipe? It looks a lot like that right there. Okay. You guys write the formula for the tension of the string, which is equivalent to maybe the weight of this hanging, that hanging weight right there, as a function of the swinging mass, the tangential linear speed, and also this radial size. So, right, this string tension as a function of this m, this v, and this r. And what does that equation look like? All right, everybody got that formula? You guys all read it? What'd you guys write? mv squared over r. Right? So mv squared over r. Now I'm saying Fc for centripetal force. But if it's this particular story, it could be this tension force here, or it could be this hanging weight that you could do. Something like that. Now, guys, the centripetal force equals mv squared over r. Interestingly, is not exactly on this page, but it's sort of the centripetal acceleration is. You guys see just plain v squared over r? I mean, if you divide by the mass, that would give you an acceleration, right? So it's right here. It's about a third of the way down the page. You see, a is v squared over r. Right? So you got that. You have this one, but not this one. Right. Now, really, this is only an approximation for the scenario. I remember you had a textbook version that had this top mass actually on a table that was frictionless, which actually this would work a little bit better for. Okay. Now, you guys were assuming the string is horizontal, which was approximately true, but not exactly. It was probably realistically hanging down about 5 degrees, something like that. Okay? Because what if the strain was hanging down significantly? So you couldn't actually approximate it very well with this. Like, what if this angle was like 45 degrees, right? And that would be more like a conical pendulum situation, which I got right here. Right? So this is a more realistic example. Or if you just slowed it down, maybe it could look more like a conical pendulum. Conical meaning like a cone. Could you guys imagine that the string would make a cone shape as it's going around? Right? Now, I want you guys in your notes right now to set up two formulas. And as you're looking back to your notes a few weeks from now, it might help to sketch out this diagram real fast or write conical pendulum. Right? I want you to write two formulas that are going to go hand in hand. Because what is the what's going on horizontally and what's going on vertically? So write a formula for the horizontal force or force components, and write a formula for the vertical forces or force components. Okay, go ahead and do that. Write those two formulas, like a system of equations. Aha, yeah. All right, you guys write a system of equations. Okay, what's going on horizontally and what's going on vertically? Okay. I'll throw a hint at you guys while you guys are writing those. So, guys, what is the net force in the vertical direction? Just in the vertical, strictly in the vertical. What's the net force? Guys, is that mass moving up or down? No, so the net force vertically is 0. Right? Guys, the net force vertically is 0. Right? Now, is there a net force on that mass?
Yes.
There has to be, yes, because it's on a curved path. Right? Right? But the net force is only which direction? Horizontally. So when you set up a horizontal equation, there is a net force. When you set up the vertical equation, there's 0 net force. Yeah.
Wait, if it's on a curved path, that would mean it goes down. Isn't there some vertical?
Well, it's on a horizontal circle. See this dashed circle right here? That's the horizontal path it's on. It's just a horizontal circle. Yeah. And so it's not actually moving up or down. As long as you keep it at a constant speed, that'll be true. Constant linear speed. All right, guys, got these two formulas? Okay. I've seen AP ask a FRQ on this in the past. I forget if it was one of their practice materials or if it was the real deal, but I've seen it show up before. Okay. So here's what I'm looking for. Oh, no, there's two forces. Like there's two proper forces on this mass. There's its own weight pulling down, and there's this tension pulling at an angle. And it looks like I've defined the angle relative to the vertical. I think it's usually given that way. That's in contrast to, I could have given you this angle down here from the horizontal. That would be the complementary angle. Like here, guys, if this theta is 50 degrees, then what would this angle down here be? 40 degrees, right? Because this 40 and this 50 would have to add up to 90. Plus this 90 gives you 180 for a triangle. Okay, because I see some triangle geometry there. Right. Right, so I'm playing off the vertical angle. Oh, I know vertically the forces have to zero out. Hey, that's this top formula here. Isn't this the vertical force equation? So I take the string tension right here and say times cosine of this angle. That gives me this vertical component, right? This would be adjacent to the angle. That would be the vertical component, right? I subtract off the weight, which is down. That has to zero out. Wouldn't that be true? Right? So that's one of your two equations. The other equation is switch over and say, well, what's going on horizontally? Now, horizontally, there is this net force. And I got kind of a parallelogram set up here. But you could add these tip to tail. You guys, could I take this tension vector and slide it tip to tail with this weight vector right there? It gives me this net force. Or vice versa. I could take this weight and slide it tip to tail with the tension. Gives me the same net force. Right? This is the resultant right here. Okay. Right. So horizontally, there is a net force. Okay. And that is this tension force times sine of this angle. Because sine would flip over to opposite. That'd be that right there, wouldn't it? Okay. Now here's another thing you can say. Guys, what is this net force? Can you guys think of an expression in terms of M, V, and R that this net force is equal to? MV squared over R. The net force is the centripetal force, isn't it? That be the case? Right. As long as the speed is constant, this radial size is constant. Okay, get that? Okay. Now, this poster, I've just looked at that system of equations. I haven't exactly solved for anything because I found in the past this could be good quiz questions, but well, sort of like here, just throw an idea out here. if I tell you guys the some values like the speed of this and the radius of this, it gives some values, right? And I have you solve for theta, it actually turns into kind of a complex puzzle. And the best you can do is I forget exactly this expression. I think it's like sine tangent or sine cos, or there's some things you multiply together. It's kind of hard to extrapolate the data without like opening up an Excel page and doing trial and error. Yeah, but you can play around with the system equations and solve for stuff. Oh, guys, how about this? Guys, suppose I change this mass out from this little tiny mass here to this big old mass right here. So I increase the mass. Guys, if you increase the mass, do you have to swing this faster, slower, or the same speed to maintain this radial size? I think the mass ends up canceling out. Right? So as long as this mass is significantly more than the string, like if the string is negligible mass, right? It doesn't actually matter what this mass is. Now it'll show up in your equations. Like the tension would change, right? Like a heavier mass would correspond to a larger tension. Okay. But in terms of how fast you have to spin it for some radial size, it ends up canceling out. Okay. So thank you. Okay. Ooh, now here, I'm gonna backtrack a little bit. Okay. Let's go back to the simplified version. Okay. So assuming this is horizontal again. Okay. And what if I want to express this not in terms of linear speed? What if I want to express this whole equation in terms of angular speed? Like I want an omega here. Okay? And I'll give you guys a hint how to do that. You have to combine this formula here with turntable physics. You guys know that? Guys, can you substitute this v equals omega r into that v right there and resolve? Try that out. See what you get. Solve this formula in terms of angular velocity, like in terms of radians per second. Go ahead and do that. So a little substitution, a little bit of algebra cleanup. Okay. So solve for centripetal force in terms of angular velocity rather than linear velocity, or angular speed rather than linear speed. All right, got it. Ooh, almost, and then you need a second R. Okay. All right, you guys are just doing all right here. All right, solve it in terms of, okay, here we got. Make sure. Okay, guys all doing all right. Everybody's got some paper to work with. All right, what you guys come up with? F equals what? M omega squared times R, right? Because if you substitute for this V, if it's omega times R, okay, the omega gets squared, the R also gets squared, and doesn't one of the R's cancel out with this R down here? But you still have an R left over, okay? Is that true? Okay. And the end result is this O'Neill cylinder formula right here. Okay? If you did it correctly, then this is what you get at the end of that. Okay? So centripetal force is M omega squared times R. Okay. So O'Neill cylinder is you got this giant cylinder in space where there's no significant gravitational force nearby. Like here's the Earth way in the background, right? So it's just not really affected by that. Okay, but if you give this a spin, then don't all these people feel like they're walking on ground as if there is gravity? In fact, if they close their eyes and if this is big enough, it might be kind of hard to distinguish this from true gravity. Right? Really, there's a normal force from the wall holding them in, but because law of inertia, they want to fly off tangent to their motion, and the wall's holding them in. Okay? And this would be the normal force from the wall, wouldn't it? Okay? So the more massive each individual person is, the more that normal force is holding them in. The faster this thing is spinning, the more the force is. Right? In fact, that's a squared relationship. Here, guys, if this was spinning 3 times as fast, what would the artificial gravity be? It'd be how many times as much? 9 times as much. You see that? 3 times as fast is 9 times the. Okay. And then interestingly, like if you climb up this ladder and climb back down the ladder, the artificial gravity is very simply proportional to your distance from the center. Right. This is more useful for cases where like there's a whole rigid body that's turning, like a turntable. If you have a turntable, you might want to use these formulas. If you have a single point mass on a string, it might be more convenient to use this form. Right. So like these, of course, tell the same story, but they might be more convenient in different type scenarios. Okay. All right. Let's take out here. Ooh, actually, this is a perfect setup for the next one. So I got a turntable. It's rotating about this central vertical axis. I got a coin on this turntable. Give this a spin. Now, guys, what force is actually holding this coin on this turntable? Friction. Yeah, friction force. All right, here's the full free body diagram. You might be asked to draw this free body diagram. Weight, normal force, friction force. This whole thing is spinning. Got some angular velocity. Okay. And this coin is still in radial distance r from the center. I put it over here just for space on the page, but really this is r right here, right? Okay. Okay. Oh, guys, come up with a formula for here. I'm gonna spell this out because this one's a little complicated. Okay. Find coefficient of static friction in terms of. Okay, let me pick up my answer. Okay. Angular velocity, radius, like radial distance from the center, and also the gravity field of the planet ends up showing up. So AP would write, and any universal constant, or any physical constant, sorry, that's what they say. Any physical constants, you say, okay, that probably refers to gravity field. Okay, go ahead. Find the coefficient of friction. So here's the lab version. You guys did this lab a few months ago. So you give this a slow spin and the coin stays on. Okay. Then you give it a little faster spin and the coin still stays on. Then you spin it faster and faster and faster. And at some point, it's spinning so fast that this coin breaks friction and slides off. Right? And right at that moment, you say, okay, well, how fast was it spinning this? Just where it was barely able to hang on. And then you can apply some formula and you can determine the coefficient of friction. Right? Oh, you know what variable I did not put on here? That might show up in your middle steps. What guys? What did I forget to write here? Yeah, maybe the mass of the coin. Right. The fact that you did not write the mass of the coin, do you think that ends up canceling out at the end? Yeah. Okay. So maybe the mass of the coin can be in your middle steps, but the mass of the coin does end up canceling out at the end. So it doesn't matter. Is it a small coin or a big coin? Okay. Now it does matter what the coin is made out of. So if it's made out of copper or if it's made out of nickel, right? That'll make a difference because this would have different coefficients of friction with that table surface. Right? But the actual mass of the coin ends up canceling out. Right. So what is the coefficient of static friction in terms of all those variables?
That's what y'all make.
All right. Oh, is that Jack got it? Okay, I think Jack got it. Alec got it. Right, Jack and Alec got it. We got. Yeah, Hector got it. Get here. Oh, yeah, Landon got it. Hans got it. All right, I think some of you guys are close. Working on it. Working on it. Getting there. Let's see, who else is getting this? Okay, I think some of you guys are close. Okay, I hope I'm not missing some of you guys. So sorry if I missed you if you got it. But looking around. Okay, let's see. How about over here? Okay, yeah, and I may have missed a couple of guys, but some of you guys got this. All right, so let's go through the full process. What do you think is probably a good first couple steps here? Let's see, what did I put here? Okay, so I've got the friction forces acting as a centripetal force, and then here you go. So friction force could be coefficient of friction times normal force. Okay. Now, if we're chasing down static friction, really this is an inequality. But if it's at the breaking point, if I actually make this omega like omega max, then I could just change this to an equal sign. Is that okay? Okay. And then centripetal force. Oh, hey, here's the O'Neill cylinder version of that involves the omega. Right? Will that be true? All right. So we got that set up. Right, that's okay. Guys, what's the next step? Yeah, I'm going to substitute normal force is equivalent to this mg right here. Right? There might be a little bit different ways to get to the end. So if you do a little bit different process, it's probably okay as long as you got the you have the correct setup and the correct answer. Okay. Okay, yeah, that's exactly what I did next. Okay, this normal force is equivalent to this mg. Okay. Ooh, and now what happens? Now mass cancels. So I told you mass was going to cancel, and there's a step where it happens. And what's the very last step? Yep, divide the g down. And there's your answer. Okay, so omega squared r divided by g. Oh, yeah. Okay, so the question is, if this shows up as a free response question, which it very well could, if you don't have an inequality, if you have an equals, would they give you credit or not? Well, it depends how they word the question. So if they word the question as or if they tell you that this omega, this angular velocity is like maxed out, and if you were to spin it any faster, then it would break friction side off. Then you can just hit equals here. Yeah, you can just hit equals. Right. If they have it as a generic case where they're spinning it slow and a little faster and a little faster, and the coin is just eternally stuck on, and it's like we never even got to the point where it was about to slide off, then definitely make this an inequality. Okay. Right. Yeah.
Is Archimedes' principle the conservation flow? Is that a difference?
Archimedes' principle tells you the value of the buoyant force. So you can have static water.
Pascal's just
Pascal is like equal pressures, like pressures transmitted and diminished. Yeah. Here. Here. So yeah, we got some side questions here. Let me just go ahead and knock those out real fast. So on your orange banner posters, I know you guys got little thumbnail versions. So question about fluids real fast. Your conservation of flow is cross-sectional area times speed is the same everywhere in a system. Okay. Bernoulli, if you get a Bernoulli question, you probably want to start with conservation of flow just to figure out the speeds. And then you can figure out what pressures are at different locations. So changing height changes pressure, but changing speed also changes the internal pressure. Okay. So that's all built into Bernoulli. Archimedes is the one, where's Archimedes? Oh, here it is. Tells you the value of the buoyant force. So the upward force that keeps you afloat in a pool. Okay. It's equal to the weight of water displaced. And then Pascal's principle is one that says that pressure is transmitted and diminished. Right. So like hydraulic lift, right? Force over area is the same everywhere. Okay. Yeah. Right, so got a little peek there. All right. So you guys got so far. That's far. All right. So back here. Ooh, I like this next one. I like it. So, do you guys remember one day? Here, do I have this cup here? Do I have a? Here it is. Here it is. Right. You guys remember I had a cup on a string and I put some water in here, and then I was flying this around in a vertical loop. You guys remember that? Okay. And if I got this going fast enough, the water stayed in the cup. Right. And also there was some tension in the string too. Right. And then a little slower, a little slower, a little slower. And at some point it was going to be an OSHA hazard, and I was about to make this place all slippery. But if I was spinning it fast enough, the water would stay in the cup. What's the minimum linear speed to get around the top? Do I have the answer in terms of linear speed? Yeah. Okay. I have the answer on this poster in terms of linear speed. And there's also an angular speed conversion you could do, but let's just stick to linear speed because that's what I got on this poster. So what's the minimum linear speed at the top? I'll just leave that really open-ended. Okay. What could that be in terms of? Does it have anything to do with the mass of water in the cup? Does it have anything to do with the radial size of the circle? Does it have anything to do with the gravity field of the planet? It probably has to do with two of those three things I just mentioned. Okay. So what's the minimum speed? Right. Of course, there's only variables up there. There's no numbers up there, right? It's all variables. So what's the minimum speed to make sure that the cup gets around and the water doesn't fall out of the cup? Okay. Here's a different ways to phrase that question that would give you the same answer is, guys, if it just barely got around, then what would the tension in the string approach? 0? Ooh, maybe that could be helpful, right? If there was like just barely 0 tension just at the top for 1 instant, that could correspond to that. Okay. Another application of this too is as well if you're on a roller coaster, you go through a vertical loop and you don't want the roller coaster to fall off the track. Is that also this? Yeah, it's the same thing, right? Except it'd be more like a normal force, but the same concept. Okay. There's some minimum speed to get around. Okay. All right, let's see. Aaron's got it. Okay. You guys got it? Yeah, working on it. Let's got it. Wait, what's this there? Ooh, close, I think. Close. In terms of variables, such as v equals something. Guys, there's no numbers in the solution. There's no numbers on that page. It's all variables. It's all variables. All right, who else has got this? Getting there. You got it. Oh, wait. And what's the square root of v squared? This is v, right? V equals square root here. All right. Yeah. So Alec got it. Yeah. So that's lowercase g, right? Yeah. So Aaron got it. Alec got it. Who else got it? Yeah. Hans got it. All right. How about you guys? Get working on it. How about over here? Okay, that's the angular version. So if you did omega, that'd be all right. All right. So I know a few of you got it, and I may have missed a couple of you guys. So. Okay. All right. So maybe what's the thought process? What should I start with at the very top? What's the guiding principle? Yeah. The net force would be the centripetal force, which could be the weight and the tension, except actually, maybe I overcomplicated this because you guys told me that if it just barely gets around, the tension at the top is equal to what? 0. So this bit just goes away, right? So the centripetal force would be provided only by the weight, right? Only by the weight. Right? Now here's where this could branch off one of two ways. If you wanted to find the angular velocity, you can call this m omega squared times r. But I'm leading you guys towards linear velocity. So that'd be mv squared divided by r. Okay. Now what? Yeah, the m cancels. So it doesn't actually matter how much water was in the cup. Okay? As long as it doesn't really affect the radial size significantly. Okay. Yeah, the mass cancels. So the box is the next answer. So, okay, the mass cancels. You can cross multiply r. You take the square root to solve for v. And what does v equal? Yeah, square root gr. There you go. Square root gr. Okay. Now, if you had solved for omega instead, here, show you guys two ways to do that. You could have gone m omega squared times r equals mg. The m still cancels. And omega then would be square root of g divided by r, right? Wouldn't that be true? Okay. Or alternatively, you could start from the solution, because I know v equals square root g times r, because that's what I got right here. Right. I could substitute. I could say, I know that omega equals v over r. Isn't that true? From turntable physics. Right. I can, whoops, actually, I meant to go the other way around. V equals omega times r. Right. I can take that, I can substitute it, boink, right there. Sure. Right. And then that would look like this. Omega r equals square root gr. Right. I could divide the r down. Omega equals and square root. So that'd be gr over, and if I put that inside the square root, that'd be r squared inside the root. One of the r's goes away. Omega equals square root g divided by r, which is the same thing as I got up here. It's the same thing. Okay, you see that? Right, is right? Right, so that's in terms of angular velocity, and this one's all in terms of linear velocity. Right, you guys good with vertical loop? Vertical loop. Okay, nice. Here, this one I'll show you guys. So if you keep a track, there are lots of different types of acceleration. The first acceleration you guys learned way back in like August, September was tangential linear acceleration. This is just the rate that you're speeding up, like in a car or something like that. And this is also related to Newton's second law of motion at equals ma. That's this green one down here. Okay. Then when we got to turntable physics, you say, well, the turntable could speed up or slow down spinning. That's alpha angular acceleration. That's this one here. Right? It has these connections. Okay. And then there's also that centripetal acceleration. That's this one here, which is like v squared over r, like that. Okay, so different types of accelerations be different things at different units. Okay. Meters per second squared, radians per second squared, and back to meters per second squared. All right, what's next? Yeah, here, I'll just show you guys this one too. Okay. But guys, here's 16 different questions that could be asked. You guys see 16 different questions that could be asked from this page? Okay. Guys, here's a Ferris wheel. And the idea of a Ferris wheel is its constant angular velocity, right? Constant angular velocity. Versus if you have a ball on a string, do you think the most realistic assumption would be that it's speeding up on the way down and slowing down on the way up, right? Unless they say otherwise. I've seen them say assume constant speed, but that would be kind of weird, right? Naturally, you should expect it to speed up on the way down and slow down on the way up. Right? So what are the forces going on? Say if you're inside this carriage and the Ferris wheel versus a ball on a string, what are the forces? Okay. So let's start with the Ferris wheel. A Ferris wheel, you always have your weight down. You guys see this green weight vector going down? Right? So you're always like sitting on a seat. Right? And there's some normal force on the scale. Suppose you're sitting on a bathroom scale on the Ferris wheel. Let's say it's spinning around pretty quickly. Zoom, zoom, zoom. Do you think you feel pretty heavy down at the bottom? Yeah, because the scale is really pushing up on you, so that there is a net force. And the net force would be the centripetal force, m omega squared times r. Right? And at the top, you feel kind of light. Right? Feel kind of light. In fact, this is spinning too fast, maybe you kind of like fly off your seat. Last ride of my life. And then going around the sides, Now there would be some sideways force. I didn't really label it, but maybe some kind of friction force to hold you in, possibly. Right. Right. Now a ball on a string. Well, we just did this one right here. Right. Oh. And then at the bottom of the circle, there'd be a huge tension string that's definitely more than the weight of the ball. Right. And then you guys see how the tension and the string is always going to point towards the center of the circle, right? And the weight always points down. Right? So the net force is always changing on the ball and the string. All right. All right. And over. Okay, we got about a minute and a half left. About. Okay. So here's a car going over a valley, car going through a over a hill and through a valley. So the weight of the car is the same everywhere, but the normal force on the road holding up is changing. You guys see, you could put a circle right here, have some radius of a circle, and same thing here. This valley could have some radial size circle. You can fit a circle right here. Okay, so there's some kind of centripetal application. If you find the net force on either one of these, this normal force minus this weight, or in this case, this normal force minus this weight, right? You can get the net force, which is the centripetal force, to keep it on a circular path, like a vertical circle. And this one's a little involved, but this is going to be our good pause point poster today. Is what if a car's on a bank track? You have to think in 3 dimensions. So isn't this car going like into the page as it's going around on this bank track, like a race car, right? Hey guys, this one's pretty involved. How many forces are on this car? Yeah, I see 2 forces. The weight pulling down and the normal force up to the left. Now there's possibly a friction force, but let's say we get rid of friction. Let's say the road is iced over. So if the car goes too fast, it's going to tend to kind of move up the incline. If it's moving too slow, it's going to kind of drift down. But that's only because it has inertia like moving into the page. So you have to think in 3 dimensions. Right. Anyway, there's a lot going on with that one. I remember AP gave you a multiple choice question about this. It said if you increase tan theta by a factor of 9, that B would have to increase by a factor of 3, something like that. All right, so hey, close down this recording. You guys have a good day, and I hope you guys do well on the SAT.